surface integrals, and the definition is a surface R vector that is equal to small f vector which is depending upon u and v. This is called smooth if this f vector possesses continuous first order partial derivatives, right? Second is a normal surface integral. Let f vector that is depending upon this R vector be a continuous vector point function. Now what is a vector point function? A function that assigns a vector to each point of some region of the space. For example, if this is your region R, right, and suppose this be the point x, y, z, right? If to each point x, y, z of this region R in space, there is assigned a vector f that is depending upon x, y, z this point, then this f vector is your vector point function. That is to assign a vector to a point which is present in this region R, right, to each point, right? So if this f vector which is depending upon this R vector be a continuous vector point function, and let the smooth surface be R vector that is equal to small f vector which is depending upon u and v, right? Let's consider this surface S which can be closed or not, right? So consider any portion of the surface be S, and to distinguish between the two sides of the surface, I'm taking this side of the surface to be as S, right? And I'm going to divide this surface into many subsurfaces, and let me consider this subsurface, and I'm taking a point in the subsurface to be as VP, right? Let VP be the point in the subsurface, right? And let NP is denoting the unit vector which is along the normal to the subsurface at the point VP, right? So NP vector is your unit vector along the normal to the subsurface where the point VP is present. Now for this subsurface to which the point VP is present, let me take the area of this subsurface to be as delta SP, right? So this is the magnitude of the area of the subsurface. So your delta SP is the magnitude of the area of the subsurface, right? Now if I multiply this delta SP with the unit vector, that is NP vector, then I'm getting the vector area of the subsurface, right? And let me denote this vector area of the subsurface with delta AP. So here delta AP is the vector area of the subsurface, right? So then delta AP vector, that is the vector area of the subsurface, this is equal to multiplying the area of the subsurface, that is delta SP, with the unit vector which is along the normal to the subsurface where the point VP is present. That is why I'm writing AP, NP, SP, because that point VP is present over there, right? So the vector area of the subsurface is equal to the product of unit vector and magnitude of the area of the subsurface, right? Okay, if I take the dot product of delta AP with F vector which is depending upon VP, the point VP, right, and consider their sum. So that is what is in the next step. Consider the summation F vector VP, its dot product with delta AP vector. So this summation is equal to, now this summation is extending to the various subsurfaces in which the surface S has been divided. The summation is extending to all these various subsurfaces, right? So this summation is equal to summation F vector VP and delta AP is this. NP vector multiplied with delta SP, the magnitude of the area of the subsurface. Then the limit of the sum when extending to all these various subsurfaces, and if these number of subsurfaces are reaching infinite number of subsurfaces, then obviously the area of each subsurface will be tending to 0. Yes, if you go on subdividing this surface S, and if you are getting the infinite number of subsurfaces, then obviously the area of each subsurface will tend to 0, isn't it? So the limit of the sum when number of subsurfaces are infinite, then the area of each subsurface will tend to 0. Then this is called the normal surface integral of F vector over S, right? And is denoted by integral of F vector dot dA vector across S, fine, which is equal to integral of F vector, its dot product with what is dA? It is n vector ds, right? This is your vector area and this is your magnitude of the area which is multiplied with the unit vector, right? That is equal to your vector area of the subsurface, fine, across S. So this is your normal surface integral, right? One thing more, the value of the integral will change in sign, but not in magnitude. When we carry the integral on one side then on the other, right? For in that case, in each term the sign of NP vector would change, right? If I write this F vector into its component, suppose this F vector is depending upon x, y, z, writing its component as F1 x, y, z I cap plus F2 x, y, z j cap plus F3 x, y, z k cap, right? Then integral of F vector, its dot product with dA vector is equal to the integral of F vector. What is dA? It is n vector into ds, right? And this is equal to, this will change into the double integral across S, and that is F1 x, y, z, and we write here dy dz, then F2 x, y, z, and we write here dz dx plus F3 x, y, z, and writing here dx dy. Please mark this as 1. Now by the rule of change of variables for integrals, this integral 1 can be rewritten as ordinary double integral, that is F1 curly yz divided by curly uv, right, plus F2 curly zx divided by curly uv plus F3 curly xy divided by curly uv and du dv, the product. Now as what is your Jacobian? Curly yz divided by curly uv, and this is equal to the determinant of, yes, curly y over curly u, curly y over curly v, curly z over curly u, curly z over curly v, right? So this implies what is dy dz? It is Jacobian multiplied with du dv. This is the formula, right? So that is equal to curly yz divided by curly uv du dv. Please remember this. Then is the definition for the flux of f vector. So the definition, the integral of f vector, its dot product with dA vector over S of a continuous vector point function f vector over a closed surface S. This is important to note. This is called flux of f vector across S. Okay, second definition. Let vector element of the area is equal to, if I take the vector element of the area to be as ds vector, let the outward normal vector at P of the surface be n vector. And if the element of the area at P be ds, this is your element area, right? Then vector element of area ds vector will be equal to, yes, element of the area at the point P is multiplied with the outward normal vector n. Yes. Then by surface integral of f vector over surface S, we have, yes, integral of f vector, its dot product with ds vector over S or across S, which can also be written as, instead of ds we can write, or integral of f vector, its dot product with, yes, n vector multiplied with ds across S. Or simply you can write this as integral of f vector n ds across S. Fn is denoting the component of f vector in the direction of the outward normal at P, right? So this integral can be written as, finally, for flux, right? So it is integral of f vector dot product with ds vector across S is equal to integral of f vector, yes, for ds vector we write n vector ds across S, right? This is your integral which is known as the flux of f vector across S. So note, integral of f vector dot product with ds vector across S is equal to integral of f vector dot product with n vector ds across S. Right. Alright. Thank you. Stay blessed.